Okay, good morning everybody. I'm glad to be here at the philosophy section because if you want to do fundamental physics, I think that what today is called fundamental physics is mostly either mathematical fantasy or experimental high-tech sport. So if you really want to bother with the problems of Einstein, Dirac, Schrödinger, or Ernst Mach, you better call it natural philosophy. And I'd like to convince you today that the best way to approach fundamental problems in physics is to consider fundamental constants of nature. That's actually what Einstein also proposed. He said numbers arbitrarily chosen by God do not exist, and that their alleged existence relies on our incomplete understanding. That, by the way, does not relate only to numbers, but that's an important statement because I think that constants of nature in some way have replaced today the Godhoods, okay? The Godhood was something you could not explain, a natural phenomenon, and now we have so-called constants of nature we don't wonder about. We sometimes explain it as unexplainable. We declare them as unexplainable because our understanding is just limited. So the question is, what is a fundamental constant? And for this talk, I would like to start with a very general definition, which might be surprising, but just take every observed number, every quantitative measurement as a constant of nature. Of course, you may call it measurement value, you may call it free parameter, constants of nature. It's basically all the same thing. But if we're doing physics, we're trying to find laws, we're trying to make sense of our data, right? And these laws more efficiently describe the data. So when you have found out something, you have a more efficient, a more parsimonious description of data. And so I would like to convince you that every progress in physics means reducing the number of free parameters, reducing the number of fundamental constants. And I think if you look at the real big progress at the scientific revolutions, there is quite a general pattern you can observe. The first step is a visionary idea, usually that unifies different concepts which were unknown to be related before. And then, of course, you need mathematization to be quantitative, you need equations, and this process ends up with the elimination of one or more constants of nature or one or more measuring values. So all this is best explained by examples, and I will go a little bit through history here. And take Newton's law of gravitation. The important step, the important visionary idea not to forget was, oh, mundane and celestial gravity have the same origin. That's really a great idea. And then it took years and years to deduce that inverse square gravitational law. And you see, I mean, that little g, that could well be considered a fundamental constant before Newton, because it fundamentally tells you something about nature, how fast objects are accelerated, okay? So now this revolution, what does it do? It explains this little g by a much more general concept, the big G and the mass of the Earth and radius of the Earth squared. So we get rid of one constant. That's the big progress of Newton's law of gravitation. You have the elimination of, back then, important constant of nature, which is of course not important any longer. Totally different field, thermodynamics. The great idea of Robert Meyer was, oh, temperature is nothing else but kinetic energy. Okay, Meyer was even wrong with the equation. Okay, but then if you work it out, so at this point, K before was an important constant of nature. It told you about heat and temperature. So, but once you understood this equation, it's not important any longer. It's eliminated. It's just a matter of defining temperature. Electrodynamics. Light is an electromagnetic wave, one of the biggest revolutions. I mean, modern technology would be unthinkable without that. What's behind? Behind is a revolutionizing equation which relates the electric and the magnetic constants to the speed of light. And that's how, of course, you need also Maxwell equations, but that's the equation that eliminates one constant of nature. Planck's law of radiation, another example. It was well known, Wien's law and Rayleigh-Jean's law, the two, and Planck just put it together. He had the unifying idea, oh, that should be one important law of thermal radiation, and that's how he arrived. He had two constants before, in the Wien's law and in the other law, and now it's just one H. That was the discovery of H, or he first mentioned H in this context. And, well, another important historical event in atomic theory was Johann Jakob Balmer. Okay? In 1885, he investigated the spectral lines of hydrogen. And his idea was just great. There could be a simple mathematical relation behind these numbers. That was a spectacular idea, a visionary idea of unification. But he needed to work out, and he arrived at this equation with Rydberg's constant. And you know, this is a dramatic reduction of the constants of nature, what I called before, because every spectral line of hydrogen would be a measurement value that tells you something about nature. And now it has become so simple, you just need one constant. 3 decades later, Niels Bohr came up with the visionary idea that H, interpreted before by Einstein, acts as an angular momentum of the atom. That was the visionary idea behind all this development of quantum mechanics. It needed a lot of working out in equations and Schrödinger's equation and so on. But the equation that actually reduces the number of constants is this. You have Rydberg's constant measured back then by Balmer, and now you express it by other known constants of nature. So you end up with one less constant. I could go ahead for a while here because, I mean, H appears in different contexts in quantum mechanics, and somebody stumbled upon a strange effect. He could potentially have invented a new constant of nature, but H was already there, so you didn't need that. But all these are simplifications because you had this insight, this relation to H. Now, also relativity, even if it worked a little bit differently, the idea was, okay, the speed of light is relevant for matter. It's not nothing self-understandable. It's an insight you had to have, and then of course there's m equals c squared, e equals mc squared, and the time dilation and so on. And well, c was not eliminated, but imagine that Einstein hadn't developed special relativity, and people stumbled upon time dilatation and relativistic mass increase. They would have invented other constants, and then somebody came along and unified it and reduced the number of constants. Now we come to the revolutions that have not taken place yet, and of course there are important questions, open questions. Nobody can calculate the fine structure constant, and a proper understanding, even there is an established theory of quantum electrodynamics, but a proper theory of quantum electrodynamics that really deserved the name would calculate the fine structure constant. There is no question about that this revolution has not taken place. And Feynman expressed quite clearly, it's one of the damn great mysteries of physics, a magic number that comes to us with no understanding by man. You might say the hand of God wrote that number, and we don't know how he pushed his pencil. We know what kind of a dance to do experimentally to measure this number very accurately, but we don't know what kind of a dance to do on the computer to make this number come out without putting it in secretly And he says, all good theoretical physicists put this number on their wall and worry about. Okay? I think we should not forget these open riddles, and Dirac was even more acute when somebody came along and presented a new theory to him. His first question was, sorry, can you explain the fine structure constant? No? So see you again when you have done it. Goodbye. So what I want to say, this very important question considered by these physicists, and of course there are other open questions to be resolved. We have a lot of numbers that are to be explained. Dirac spent, I don't know, 2 or 3 decades of this life to ponder about the mass ratio of electron and proton. And he said, it has always been the dream of philosophers to have all matter built up from one fundamental particle. So it is not altogether satisfactory that we have 2 in our theory. You know, Dirac was not satisfied because he had 2 elementary particles. Guess what he would have said about today's situation. I cannot imagine a theory containing an arbitrary number which could have been chosen by the creator in just another way. That is a similar statement. But I would like to convince you that maybe it's not easy to make progress in physics, but there is an easy measure of progress in physics. It's just the elimination of free parameters. Once we explain away a constant of nature, we have done big progress. And that's the way how it works. By the way, I don't think this is a fancy of mine because I like simplicity in physics or whatever. I think we have pretty much historical evidence that this is the way the scientific revolutions worked in physics. So, but a caveat, elimination of a fundamental constant does not mean sweeping it under the rug. There is some fashion to set all physical constants to unity and do some calculations, but that's dangerous because you're missing the real problems. I mean, there's still something to wonder about, the remaining constants, and you should not do that if you want to do fundamental physics. Another statement floating around is only dimensionless constants have a fundamental meaning. This is completely nonsensical, you know. I mean, should we stop now precision measurements of big G, or should we stop measuring H because somebody said only fundamental constants have a fundamental meaning? No. I mean, of course they have. Yeah? And if we want to understand fundamental physics, we still have to wonder also about these other constants. Not because it's 6.6, it could have another number, but the very fact that these constants exist, the very fact that there is a limiting velocity in nature tells you about something about nature. And also the things like considered unimportant, like the size and the mass of the elementary particles. Look what Einstein said. The real laws of nature are much more restrictive than the ones we know. For instance, we did not violate our known laws if we found electrons of any size or iron of any specific weight. Nature, however, only realizes electrons of a particular size. Okay? So there is some message in it we haven't discovered yet. And yeah, well, just another, unfortunately, I think there is very much nonsense floating around regarding fundamental numbers. For example, I mean, if you declare that no fundamental constants exist really, of course you don't have to wonder about it any longer, but that's not the prudent approach to take. Rather, we should think about fundamental constants as free parameters, because there's no essential difference, and think about the mechanism of science Thomas Kuhn described in his famous work, The Structure of Scientific Revolutions. And he said, okay, you have an anomaly, something that does not fit in the old picture, something that would contradict the old theory, but in order to not destroy the entire theory, we make up a free parameter, and that's the way normal science works. Usually accompanied by a complication of the model. Yeah, now we are here with, I don't know how many, I have stopped to count how many free parameters and stuff, and well, That's the standard model. By the way, the standard model of cosmology is not much better. We are on the same track of inventing new free parameters there too. And if the Lord Almighty had asked me before embarking creation, I should have recommended something simpler. Was a comment not about the standard model, but about the geocentric epicycles when King Alfonso el Sabio discovered in the Library of Toledo, he discovered this ancient theory of epicycles. And well, I think even Enrico Fermi made a proper comment. If I could remember all these names, I would have become a botanist rather than a physicist. So, well, I think that the current models are quite misguided if we want to see them as fundamental progress. And there are certainly more important fundamental constants than others. I want to just pick out the important, in any case, remaining ones. It's G, C, and H, and point your attention to a very interesting idea, how to get rid of one of them. And it's actually the first idea Einstein had about general relativity in 1907, which he later developed in 1911 in Prague. And it was basically a theory of variable speed of light. He said, okay, there must be a deflection from the principle of equivalence. There must be a deflection of light in the vicinity of masses. And in a very natural way, he said, okay, let's introduce an index of refraction and make the analogy with optics from the just proved assertion that the speed of light in a gravity field is a function of position. It is easily deduced from Huygens' principle that light rays propagating at right angles to the gravity field must experience curvature. Okay? And this is not well known, but it's actually equivalent to the common theory of relativity. Either you have curved space with constant c, which is the usual way to formulate, or you have a flat space with variable c. And of course, you might think that, well, c is defined at the fixed value, but I mean, if you use this interpretation with variable c, of course, the wavelength and the frequency would change accordingly, and you won't notice speed of light, of course. Okay, I don't have time to go into details that. I recommend this paper by a physicist from Belgium, Brockett, and he did a very nice work. He looked up all the textbooks about general relativity and demonstrated that the concept of variable speed of light still lives in there. And I have shown in my talk on Tuesday that even Einstein kept to this notion of variable speed of light even in 1917, even in as long as 1920. So it's really a forgotten form of general relativity which should be reconsidered. And it was taken up, even if Robert Dicke did not know about Einstein's attempt in 1911, he independently rediscovered the possibility of describing gravity by a variable speed of light. And he made a very interesting proposal of expressing the gravitational constant by the mass distribution in the universes. That's had very much to do with Mach's principle, that had to do with the theory of Dennis Sharma, the British cosmologist. And of course, this goes back to Einstein. And it has also an important consequence for Dirac's large numbers, that there's a close relation, as I have shown elsewhere, a close relation to Dirac's theory of large numbers. And okay, and of course, if you wonder about unifying gravity in quantum mechanics, okay, there is much quantum mechanics, quantum gravity theory published, but I mean, here's the riddle. Explain the number 10 to the 39. And Dirac's idea to this day remains the only quantitative idea. If you want to do quantum gravity, you either explain Dirac's number or you're just doing poetry. Okay, this is just a relation to Ernst Mach. And well, all these people, as I said, contributed. Even Erwin Schrödinger had an interesting idea in that, which is usually not known in 1925. I'll show you where to find the references later. Let me just emphasize the most important point of this possibility. Let's go back to Newton's law of gravitation, how he discovered it. Here we have local gravity determined by a mass distribution. Here in the solar system and for our planet, introducing another constant. But look how a very natural Machian idea of this extension of this idea would work. You explain the gravitational constants by the mass distribution in the universe. And I think, I mean, you might not be convinced immediately, and you can, it's a lot to tell about the details here. But from a fundamental point of view, either you're a believer in gods or something like the gravitational constant, God-given, or you're a physicist, you want explanations. And the only way to get rid of that big G would be relating it to the mass distribution in the universe. So I think Dirac's cosmology is, well, and of course, Dirac's cosmology enters here with another unexplained riddle. I don't know if you know that he related the ratio of the electric and the gravitational force to the size of the universe. This is usually dismissed today as numerology, but as I said, I mean, come up with something quantitative, come up with something better if you want to make progress in quantum gravity. That's this thing one has to solve. There is also an aspect of unification I want to point out. I mean, Maya with this idea of temperature in a way unified mechanics and thermodynamics. Electricity, of course, was unified by Maxwell, and electromagnetism and optics was then unified with the idea of the speed of light being related to the electrical constants. And of course, dynamics and gravitation was unified by Newton, and a similar unification could be the theory going back to Robert Dicke and Einstein, unifying mechanics and optics in this way. So, an even more general point of view is Einstein said, "I'd like to state a law of nature which is based upon nothing more than the belief in simplicity, that means comprehensibility of nature. There are no arbitrary constants. That is to say, nature is so constructed that it is possible logically to lay down such strongly determined laws which only contain logically deduced constants." And that not only does relate to numbers, which of course pose a riddle, and it's important to wonder about fine structure constant and mass ratios, but every constant of nature is something we should explain. It's the job of theoretical physicists to explain things. From a broader perspective, if we believe in the existence of the speed of light and Planck's quantum age, we are believing in kind of modern godhood. So I take it, you might be amused, but I take it for granted now that G could be eliminated by that old idea of Einstein, but we still have a problem with C and H, which is certainly not easy to get rid of. And I think the correct approach to this very fundamental question is to see C and H also as anomalies, as possible anomalies in a Kuhnian sense. That means that their very appearance tells us something about, or tells us that there is a problem of the underlying theory, which is of course at that point Newtonian mechanics and Newtonian gravity. And that sounds very scary, but if you think about, I mean, the speed of light was just a curiosity in 1676, And nobody thought about it would have a deeper relevance. Even Newton wasn't aware. And then much, much later, and well, Newton did a fantastic, incredible work of inventing concepts and structuring physics and coming up with these laws of motion and gravity. But much, much later, the relativistic behavior of masses showed that there was a problem. A problem which was not predicted by Newton. So we might even say that relativistic mechanics falsifies Newtonian physics, and C was just a parameter to fix that. That should not sound disrespectful, but I mean, special relativity is a fantastic, elegant theory. But at the end, it could be a workaround not to question the underlying concepts of Newtonian gravity, which are space and time. We believe in space and time. That's Newton just said, this is an axiom. We have three-dimensional space, we have one-dimensional time. Why are we so sure about that? Is this really the only way nature could work, or is it just the most simple way for our understanding to grasp? There's no guarantee that space and time are the most fundamental quantities in nature. And well, as I said, there is no reason why matter should not be accelerated beyond the speed of light. So the very existence of C is an anomaly. That happened at the large scale, and of course it happened also on the small scale. There was a problem. Even if you look at, you might look at continuity and differentiability. Yeah? You use this math in physics, and physicists usually say, okay, if you go to small scales, you have to take into account quantum corrections. But that's an excuse. That's an excuse that Newtonian mechanics does not work at small scales. And that could be an alarming signal. An alarming signal we worked around with, again, a beautiful theory of quantum mechanics, nothing to say about, but at the very end, C and H could be anomalies that indicate that there is a problem with the concepts of space and time. I will go more into detail about that point tomorrow, but here to conclude, historically, revolutions were accompanied by a reduction of the number of constants. With the standard models of cosmology and particle physics, this number has increased. That means, from a historical point of view, the standard models are surely no progress. Setting constants to 1 is quite useless if you want to do fundamental physics, often misleading, and significant insight can only be achieved by questioning established constants. And maybe a complete theory of reality must do without any so-called constants of nature. Some of these early ideas relating to Einstein's variable speed of light are published in Annalen der Physik. In that paper, which emphasizes the relation to Dicke and Dirac. And then there is a book, a popular book, Bankrupting Physics in English, which is a translation of the Science Book of the Year back then in 2010. And there is another book, popular book expanding in German about these problems. There will be a second edition soon. And well, this is a critique of particle physics, where you go more into detail on the parameters there. And Einstein Lost Key is a summary of these attempts of Einstein, Ernst Mach, Schrödinger, Dirac, and Sharma, and tries to give encompassing idea of all these ideas. You might not be convinced about immediately about all the details, but I think that nobody can question that these ideas are related, and there would have been an interesting discussion back then if it was known that they were so closely related. Thank you for your attention.